Okay, one term in the Fourier series that deserves some special attention is the DC, or the average term. All right, this is our n equal to 0 term. I say it reserves some special attention because of the forms of the series, and in particular because of the way that the book provides its formulas, makes that term a little bit confusing. It also becomes a little bit difficult because the integrations that you need to perform at n equal to 0 also sometimes get a little bit tricky. All right, so let's just remember that we have our three representations of the Fourier series. The first was our sine-cosine version. The second was our shifted cosine version. And the third was the complex form. Now, I see that in the first two forms of it, I have explicitly what I call an average or DC term added in. I don't see that as explicitly here, although it is there, okay, in the complex form. Now, to try to understand this a little bit, let's go back to remember the visualization of how this thing kind of comes together. All right, so the idea of a Fourier series is that I can take any periodic function, so any periodic function, again, subject to some strange constraints that we're not going to talk about, but any periodic function can be represented as a sum of sine, cosine, or complex exponentials. Okay, that's our basic definition of a Fourier series. Now, that periodic function can be shifted up or down, and that's what this guy represents, is that ability to shift him up or down on the y-axis. So this is our DC, or average term. So I keep saying average. If we look at this real quick, all right, you guys should know what the average value of a sine or a cosine function is. The average value of a sine or a cosine value is, over a period at least, is equal to 0. Okay, and let's just to do that, let's visualize again what this equation is doing. So I have my DC term plus this sum of sine and cosine. So the way we visualize that is we said, okay, here's the cosine, here's the sine at the fundamental term. I take the basic sine and cosine functions, multiply them by their appropriate amplitudes, and add them to all of the other components to create the function. All right, so here's our second harmonic component, right? So here's a cosine, here's a sine. The key identifying feature of the second harmonic is that it varies twice in one fundamental period. Okay, so it varies one time, two times. Okay, if I go to the third harmonic, I see that it varies one time, two times, three times in one fundamental period. If I look at any one of these and I say, what was the average value over the fundamental period? What I see is this guy is moving around an average of 0. Okay, so the average value of each of these waveforms is 0. So this top term right here says basically take the number 1, multiply it by a0 over 2 to get the appropriate DC value or offset of the function itself. Okay, so let's just make sure we understand exactly what it means to be an average. By definition, the average value of a periodic function is this. Basically, it's the area under the curve over a period times 1 over t. All right, and that kind of makes some sense. Basically, you're summing up all the values and dividing by the amount of time. All right, so if we look at an example of this, let's say we had f of t equals 1 plus sine omega naught t. All right, remember that omega naught equals 2 pi over t, like that. So if I plug that into the average function, right, intuitively, hopefully you'll see that the average of this guy should be 1, right? But let's see, because essentially what I've got is a sine function sitting on top of the number 1. Okay, but let's evaluate. So this is the definition here. So I plugged in my f of t, 1 plus sine, notice I wrote it as sine omega naught t as omega naught. I put in there 2 pi over t, okay? Because I have the integral of two things added to each other, I basically say I'll take the integral of the number 1 first. Well, that becomes 1 over t, integral from 0 to t of dt. And then I have plus 1 over t times the integral of sine 2 pi over t little t. Okay? So the first integral is pretty easy. The integral of dt is t, and I integrate it from 0 to t. So that's this guy right here. Okay? You should recognize that that is going to be 1 over t times t minus 0 or 1. All right, so this guy is going to become 1. And then the integral of sine omega naught t, right? The integral of that dt is negative 1 over omega naught cosine omega naught t. Okay. Omega naught t like that. All right. That's what I have here. And then I evaluate that guy from 0 to t. So you should see if I plugged in cosine 2 pi capital T over capital T is cosine of 2 pi. So in other words, this guy would become 1 over 2 pi cosine of 2 pi minus cosine of 0. Cosine of 2 pi is 1. Cosine of 0 is 1. So this is simply 0. So in other words, the average value of sine over a period or cosine over a period is 0. So whatever the offset is the average. Okay? So it's sort of a simple definition of the average of a periodic waveform. Now, if I look at the complex form of the series, right, the formula for the alpha n values, the complex Fourier series coefficients, is 1 over t integral over a period f of t times e to the negative j n omega naught t. Well, if n equals 0, right, I plug in n equal to 0 into this expression, I know that this guy right here simply becomes 1. The complex exponential just disappears and becomes the number 1. So what I see from that is A0 is the same as the definition of my average. Okay? So I can see from that alpha 0 is the average value of the waveform. Now where this gets confusing is, let's look at something like the sine-cosine version of the series. Notice the way they've written A0 here. They've said A0 equals 2 over t times integral over a period. Well, that is 2 times our definition of the average. So because of the way that they've defined this equation right here, they've defined A0 to have twice the value of the average of the function. So what that means is I could write this guy as alpha 0, because remember alpha 0 was equal to the average value of f of t, plus the summation from n equal to 1 to infinity a n cosine n omega naught t plus b n sine n omega naught t. That's a completely valid way to write this expression. But because of the fact that they defined A naught to have this 2 times the average, I have to state that in this case, alpha naught is equal to A naught over 2, like that, right? Because for whatever reason, they've defined, and I think I know why they did it, all right? They defined the average, the A naught, to be twice the average so that it was consistent with the way these equations looked. So there was a 2 over t and everything. They didn't want to have another equation that had a 1 over t. Okay? So it's very confusing, but essentially the way to look at it is the average value of cosine and sine over a fundamental period is always 0. So if you took the average value of f of t, that's the average value of a naught over 2. Well, that's a constant. It's just a naught over 2, plus the average value of that sum of sines and cosines. Well, the average value of that stuff is always 0. And again, you can see that from looking at this picture here. If you took a sine and cosine over a fundamental period, even if it's a second harmonic or a third harmonic, if you do it over a fundamental period, it's always going to be equal to 0. All right, that's a really important concept. All right, and so it's a little bit confusing to relate these series. All right, and the reason is because if I look at the sine cosine or the shifted cosine, basically I see that the DC term always has a naught over 2 or c naught over 2. I just say be careful about it. All right, alpha naught just so happens to meet the definition of the average of a function, whereas the way that they've defined a naught and c naught is that those are equal to 2 times the average of the function. And so as a result, when I write the average term, I have to take that a naught and divide it by 2. Okay? So confusing. Hopefully that clears up some confusion. Everything would have been a lot simpler had the authors of the book probably just not had this 2 in this equation, right? Had they not had that, that would have made everything a little bit simpler. But they did, and so we will deal with it.